Image classifiers are vulnerable to evasion attacks, where adversarial images are crafted with minor perturbations to induce model errors. Adversarial training is the standard defense, yet it comes with a twofold trade-off: the accuracy-robustness trade-off and the robust fairness problem. As such, machine learning practitioners face a dilemma. Should they focus on accuracy, robustness, or achieve a balance between the two? To assess model trade-offs, they need to explore models on natural and adversarial datasets comparatively. We developed VATRA, a visual analytics design probe, to explore how practitioners can leverage comparative visual designs for trade-off analysis. Suppose Jian, a computer vision expert, aims to explore trade-offs of her traffic sign classifiers, trained with varying degrees of traits, an advanced AT method. She loaded 3 ResNet 101 models on the GTSRB dataset and applied PGD as her attack method. These models include Model 0, a standard model, Model 1, trained with a small degree of traits, and Model 2, trained with a higher degree of traits. Jian first selects Model 0 to assess trade-offs in standard training. From the summary view, juxtaposed metrics direct her attention between 2 contrasting values, revealing that Model 0 has high accuracy but very low robustness. Concerned with its safety, Jian compares other models with the blink interaction. By focusing on the alternating metrics superimposed in the same view, she discerns with little memory load that Model 1 achieves high robustness but slightly lower accuracy. Model 2 exhibits marginally better robustness but much lower accuracy. Jian recognizes that the accuracy-robustness trade-off persists even with advanced methods like traits. Finding Model 1 the most promising, but hoping to alleviate its trade-offs, Jian decides to take a closer look at it. She displays the global embeddings of all 43 signs in the global dual projection view. By carefully adjusting the shine-through back and forth, Jian compares between Model 0 and Model 1 by retaining both distributions in her mental model, making several observations. First, from the juxtaposed plots that highlight high-level visual differences, Jian notices that Model 1 maintains a similar layout under both conditions, meaning that it perceives both datasets as alike. Second, since this design also preserves context of the original embeddings, she sees that Model 1 relies on human interpretable features for classification, as signs with similar shapes and colors cluster more closely. However, there are significant clusterings of squares around the prediction zones for speed limit signs. By skimming across the class matrices, the juxtaposed variations in color intensity show that there is a significant fairness trade-off for speed limit signs. Linked highlighting also reveals that, though more pronounced in the adversarial dataset, the same issue exists in the natural embeddings, leading her to suspect it as the cause of the accuracy trade-off. She assigns colors to the speed limit signs to focus the exploration on them. She starts her exploration with Class 3, speed limit 60 km per hour, by clicking its natural class centroid. The class code projection view updates, showing natural embeddings as the foreground and adversarial embeddings as the background. The superimposed view helps her compare the structural shifts within one space, and the explicit instant trajectories show that Class 3 spreads into several smaller subclusters. To identify clustering patterns, Jian selects data points to examine their raw images and notice that instances within the same misclassified cluster tend to share similar lighting. Jian considers a solution using generative AI to simulate various lighting conditions, creating artificial data to enhance model robustness. Additionally, the juxtaposed before and after images highlight differences in semantic visual features, allowing her to notice that PGD alters the shapes of speed limit numbers. To address this fairness trade-off, Jian considers implementing semantic integrity checks to identify inconsistencies in visual attributes like shape, size, or colors. Jian continues to gather new trade-off insights, aiding in the development of new solutions to enhance the model. For more details on our design probe and empirical insights into comparative visual approaches for trade-off analysis, please refer to our paper.